Right. Maintenance is mostly just preventative measures and repair systems. And it's important because we need to keep the ship operational until we get to Alpha Centauri, which is about 100 years. It's not super difficult because we don't need to sustain life for that long. It's just a bunch of electronics that we need to keep in a stable environment until we get there. We don't need to provide oxygen for everyone or anything like that. And for preventative systems, the main factor here is adjusting the factor of safety. We can go really overboard with things to make sure nothing ever goes wrong. And we can also have plans in place in case something goes wrong. So, power. To manage all the turbine systems and things like that, we need to have a piping system. And this piping system, I asked him for the number, and he said the max pressure you can get for that, or max projected pressure, is 196 pounds per square inch per foot. And the type of piping I chose was the carbon steel, because it can operate at these temperatures, up to 750 degrees Fahrenheit, and still withstand all that pressure and more. These are the pipe schedules, these are the grades of the pipe, and if you pick the best grade, you can have 2,900 pounds per square inch of pressure on the pipe, and the pipe won't break, I guess. And in case it does break, due to the pipe failure, we're projected to have about 310 feet of pipe for the power generation system that we came up with so far. And we're gonna connect, we're gonna have sections that are connected by electromagnets. Just, they turn off if you want to drop the pipe, and they turn back on if you want to continue pipe. And what we're gonna do, in case something goes wrong, in case a pipe bursts, we need to pretty much shut down the turbine immediately, turn on, and close the safety valves, so the steam doesn't blow up and damage the ship in any way. So after something happens, the turbine is shut down, safety valves engaged, and then that pipe is dropped and the new pipe is brought in. We'll have like an inventory of pipes ready to replace any broken ones. And the new ones is brought in by rail. The rail lowers down the pipe a little bit, and both is secure. And that's the power we need for the rail. So I just used like an industrial rail. I didn't go super fancy at this. The single phase rail, 3 watts of power, 300 volts. And the servo motors, we just need one major motor to bring it down, and I guess 2 smaller motors to move it side to side just to adjust it. You don't need a lot of degree of freedom of movement there. So I pretty much used like motor half the power of that one. And this is based off of a motor I found on Amazon. So, and in case one of the turbines stopped working, we can't really bring in a turbine on a rail. Those things are really heavy. So his plans do have tier turbines. So if one stops working, we can just stop flowing things to that turbine, which will flow through the other two. And like you said, cooling through the ammonia loops, because that's what they used on the International Space Station. And it works extremely well for that. What they do is they just radiate all the heat away. I actually looked at some calculations for this, and if the emissivity is 0.96, which is found in titanium alloys, there's one titanium alloy, but the 0.96 number is pretty high. You can get a cooling of up to 1.6 BTU per minute per second. I think it was second. 1.6 per second per meter squared. So more surface area you get, the better. And you can increase surface area with the radiator, with the droplet thing that we talked about. And helium. We need a lot of helium to pressurize the ship. The reason we chose helium over things like oxygen is oxygen has a tendency to catch on fire, things like that. Using helium makes the ship really safe. We eliminate the chance of having a fire. It's also really stable. It doesn't melt until it's like negative 400 degrees Fahrenheit. And because we can make it, we can just expel it from the sides of the ship to get rid of it. And the way we expel it, we just have nozzles. I mean, there's the vacuum space to do the work for you. You don't need to have a pump or anything.
Well, you gotta be a little bit careful about spelling it.
We can use bays.
It puts a little bit of, I mean, what?
We can use like airlocks.
So much thrust going out of one direction. It would
No,
be
we can use airlocks and we can equally distribute it from both sides so the forces cancel out. So, and we can distribute the nozzle throughout the ship so we evenly suck out air instead of like all from one side and creating a huge vacuum. It's not. And for the hull of the ship, repairing it, this is really dependent on how we're going to shield it. But it really depends on the side it is. But if this is compatible with it, we totally should use it. And this is really new. Like MIT just came up with this like this year, and they actually haven't even released any numbers for it. But they found that some types of metals, when the grain boundaries have been broken, they'll slowly flow in and fill it. It's not as stable as we thought. Like these metals aren't as stable, and they're not as rigid as we thought. But it's like a softer metal, but the advantage is that it fills in any like deformities. So if you get a thick enough layer on it, these micrometeorites, I think the average is 0.5 grams per cubic meter in space, and we're going to be going through a lot of this.
0.5 hydrogen nuclei per cubic meter.
I just looked at micrometeorites. So.
Oh, interstellar space? Or?
Interstellar. I mean, space.
Okay.
And this would help us mitigate all that damage. And the limitation with this is that you can, I mean, it's not like regenerating metal, it's just flowing in to fill any holes. So eventually it'll thin out. If one area is getting too much damage, it'll thin out and won't be able to fill it. So that's the issue with it. But